Welcome to a brief introduction to multi-level models by Noah Love. Let's first begin with a simple example to show how regression can sometimes fail and when we might need a multi-level model to find the correct answers. This dataset was collected by asking British folk to visit a recipe website and then measure the time that they spent on that website, known as the bounce rate. This is a common website metric, and web developers typically use it to try and find ways to entice you to stay longer, engage more, and then eventually view more ads. Data points were collected in 8 counties in England from members of the public of all ages. And we can look at the initial plots and they look very nice, almost perfectly normally distributed, bounce times, as well as a very nice distribution of ages. Age, as is usually good practice, was scaled in order to be standardized, which helps with the coefficients in regression. Now, as you may have seen in your Introduction to Statistics class, we apply a linear regression. And wow, it looks quite good right off of the bat. We see a strong correlation between age and bounce time. We can then maybe begin to draw a possible conclusion that older people stay on websites longer and younger people tend to leave right away. Well, not quite. When doing a regression, it is important to check that the assumptions that we have made are not being violated. One of these is that the residuals are homoscedastic, which means that the residuals are normally distributed in relationship to the predicted value. For example, we need to make sure our predictions are equally good and bad across our predicted values. Now, our current graph doesn't look too bad, but when graphed with the difference in observed and predicted rather than just the residual, we see a systematic problem. For people around 50 to 60, this middle range, or 0 as it's standardized, the model underestimates their time consistently, whereas younger and older individuals are overestimated, as in their predicted bounce rate is larger than the actual time that they spend on their website. So something is wrong. And as a result, we must ensure that our data points are independent. When graphed by county, the problem becomes incredibly obvious. There's substantial grouping, sometimes called clustering, that has gone unaddressed. Places like London and Devon seem to be very impatient, for example, regardless of the age there. Thus, the model needs to take this into account. We can do this by using a random intercept and slope multi-level model. Here, we allow the slope and the intercept to vary depending on the group that the data is in. In this example, there will be 2 levels, level 1 being the individual and level 2 being the county. In fact, after the multi-level model has been applied and the bias is fixed, as in the residuals are much more appropriately fitted, it turns out that age does not impact bounce rate. That's right. After controlling for the random variation that is caused by counties, by which county you are in, there is no longer statistically significant differences based on age, and the primary findings that the regression found are not appropriate and some would call wrong. What we have seen in this data was that individuals in certain counties took longer on the website, and that these counties just happened to be older on average. So, what are multi-level models now that we've seen one? Multi-level models are statistical models of parameters that vary at more than one level. They sound much more difficult than they actually are, especially in theory. They also have many other names, sometimes called hierarchical linear models, linear mixed effect models, mixed models, nested data models, random coefficients, random effect models, random parameter models, and even split plot designs. But in general, people call them multi-level models or sometimes hierarchical linear models if the data nicely nests into each other level. Let's take a look at a more simple example, the more common ones that you see when introduced to multi-level models, in this case, school. In this example, imagine that you are a policymaker or a school superintendent or even an academic researcher, and you want to look at testing scores of students throughout your home state or home country, say the United States. How would you do that? It might be reasonable to think to start with a regression of students across the nation. But why wouldn't you do that? Well, first of all, it violates our assumptions that we've just gone over. These are likely highly dependent on each other. These observations are not independent. In fact, they are going to be clustered, sometimes by teacher, by school, or maybe by county, by state. Each of these different levels are going to play an important effect. Thus, we need levels or a multi-level model. Now, instead of one general random effect that predicts how each student deviates from a predicted fixed effect, so how much each individual student deviates for the national average, for example, now, in a multi-level approach, there will be multiple random effects that capture how observations deviate within a cluster, and then how each cluster deviates from the overall group. So instead of comparing the student to the national average, you'll be able to compare the student to the class, and then the classes to each other. You'll be able to compare a class to the school, and then the schools to each other, schools to the districts and to the states, and then overall the states against each other, for example. Thus, we are creating a 5-level model involving level 1 being the students, 2 being the classes or the teachers, 3 being the schools, 4 being the districts or cities or counties, depending on how your data is set up, and 5 being the states. The researcher would likely establish a different varied level. In this example, you might use test score for the student, teacher experience for the class, school funding for each individual school, and then possibly a policy score for the districts or the states. These are nested, so this is a very nice geographical example. They don't have to be. For example, you might introduce year into your multi-level approach, in which case states, individuals, and years are your 3 levels. Thus is why we usually call them multi-level models, but they can also be hierarchical. So why do we use multi-level modeling? Well, as you've seen, it's pretty great, especially at getting rid of these clustering problems and reintroducing independence. But more importantly, there's usually not a better way. We can compare a few traditional methods, several of which you can either use in the past or use concurrently as alternative ways of studying the data. First, traditional statistical techniques can be used. One could disaggregate higher order variables to an individual level, and then you can conduct an analysis from there on the individual level. For example, assign the class variables to an individual. The problem with this approach is that you would again violate the assumption of independence. This would likely introduce a large amount of bias into your results, but that doesn't necessarily invalidate them. This is usually known as the atomistic fallacy. Another way to analyze the data using traditional statistical approaches is to aggregate, work the opposite way as the disaggregation technique. Individual level variables now become higher order variables, and then you conduct an analysis on the higher level. So you aggregate. You often take averages. The problem with this approach is that you discard all that beautiful within group information, and effectively taking like the average of all the students in the class and then analyzing as much as 80 to 90% of the variance can be wasted, and the relationship between the aggregated variables is often inflated or distorted. This is known as the ecological fallacy. Another reason to use multi-level modeling is the number of predictors available. In classical regression, it would be incredibly unwise to fit so many predictors because the estimates will become unreliable, especially for smaller sample sizes. In addition, it would be necessary to leave out quite a lot of predictors in each batch as a result of avoiding collinearity. For example, you probably wouldn't be able to have so many age brackets, maybe not include all the states, regions, educational categories, or even age categories in our educational example. With a multi-level model, the coefficients for every batch of indicators are fit to a probability distribution, and therefore you can include all of the predictors in the model. Let's consider one more example in order to look at the different types of multi-level models, depending on the intercept and the slope. In this example, we look at a data set of 26 boys in Oxford, England. The height of each boy is measured on 9 different occasions, and then they're graphed and presented here. Each boy seems to be fairly linear in their growth pattern, and so a simple linear regression seems incredibly reasonable. we see that the simple linear regression fitted to the complete dataset is here. And obviously this is not a good fit. It misses almost everyone and isn't a good predictor for anyone. So we need to expand our model, make it slightly more flexible. And in this way, we need to look beyond just a group average of the boys, and we need to generalize it. First, we allow the intercept to change, and thus it's going to vary from boy to boy. We can call this change level 2, whereas level 1 was taking into account the variation between the individual measurements of each boy. The combination of the two models creates a multi-level model. The results are shown here with varying intercepts. This is also known as a random intercept model. Here, the scores on the dependent variable, in this example, the height of every single boy, is predicted by the intercept that varies across the group. This model assumes that the slopes, in this case, the rate of growth for each boy, is the same regardless of who we're looking at. Intuitively, we know that this isn't true. Kids grow at different rates, and we can see this in the example on how certain lines don't fit the general slope very well. In addition, this model has great access to intra-class correlations, so this is often what it is started with, as this is helpful in determining whether a multi-level model is needed in the first place. While this does a better job, certainly over the initial model, there is still plenty of evidence of lack of fit. We've allowed the intercept to change, but now we need to allow the slope to change. Instead of assuming a common growth rate for everyone, perhaps we can fit a growth rate for every single boy. This is known as a random intercept and slopes model. It includes both random intercepts and random slopes and is likely the most realistic type of model compared to the real world, although it is also the most complex. Of course, many times you're seeking that complexity, and a reason why so many people continue to turn to multi-level models for the ability to predict accurately across so many different clusters and layers in the data.